welcome to this explainer. Let's just dive right in, shall we? Industrial assets don't really announce when they're about to fail. There are no flashing red lights right before a total shutdown. Instead, the signals are, well, they're incredibly subtle. We're talking about slightly elevated vibration signatures, maybe rising operating temperatures, or micro leaks that a maintenance crew might just patch up before moving on to the next thing. But what these invisible signals are actually telling us is that the asset has entered a state of accelerated degradation. So today we're going to master the hidden costs behind this invisible decay and figure out how to stop the financial bleed.
Let's start by shattering a pretty common illusion right off the bat. Why do 82% of industrial machines fail long before their time? I mean, it's super tempting to think that machines just die of old age, right? That they simply reach the end of their design life and give out. But the reality is actually a lot more like a detective story. Aging equipment failure isn't caused by age alone. It's caused by the accumulation of deferred maintenance decisions, inadequate condition monitoring, and a sheer lack of structured tracking. It's a process, not a sudden event.
And the stakes of that process are incredibly high. $129,000. Let that sink in for a second. According to a 2023 analysis by Sensia Predictive Maintenance, this staggering number is the average hourly cost of unplanned downtime for industrial manufacturers. Think about that. Even if your specific facility is exposed to just, say, 10% of that figure, the economics of keeping your machines running predictably are absolutely undeniable. And this is totally backed up by Plant Engineering magazine, which points out that 82% of industrial equipment failures are random in nature, which means they're not really age-related on their own. They are triggered by operational and maintenance conditions. The absolutely crucial point here is that how a machine is maintained matters way more than its actual chronological age. Basically, if you run equipment hot or let it vibrate beyond spec, you're actively writing the script for its early demise.
Section 1. Anatomy of Asset Degradation, the Invisible Disease.
Okay, so there are 3 silent, highly technical killers of aging industrial equipment that we really need to wrap our heads around, because these are the exact forces depleting your equipment's lifespan right now. The first is metallurgical fatigue. Think of this as the baseline. Every single stress cycle, whether it's thermal, mechanical, or vibratory, adds to the cumulative fatigue load on structural components. And the math behind this is honestly pretty terrifying. For rotating equipment, doubling the load doesn't just double the fatigue damage, no way. It multiplies it by a factor of 6 to 10, depending on the material. Your equipment literally has a fatigue budget, and running it outside nominal conditions burns through that budget exponentially.
The second killer is lubricant breakdown, and this one is consistently underestimated. Oxidation, contamination by tiny particulates, thermal breakdown. They silently diminish the protective film between bearing surfaces. Once metal-to-metal contact begins, even at a microscopic level, surface wear accelerates in this massive self-reinforcing cycle. Now, if you're doing oil analysis every 500 to 1,000 operating hours, you can actually catch this. But most facilities running purely reactive maintenance programs, they don't catch it until they can literally hear the grinding. And by then, well, it's way too late.
The third silent killer we're looking at is insulation decay. So, in electrical assets, motor windings degrade slowly through moisture ingress and thermal cycling. If you aren't doing mega tests, checking the insulation resistance every 6 to 12 months, your very first sign of trouble is usually a motor just failing mid-shift. And in process industries, corrosion under insulation, or CUI, is an absolute nightmare. Moisture gets trapped between a pipe wall and its insulation, silently eating away and reducing the wall thickness by 40 to 60% before it's ever even visible on the outside. You absolutely need non-destructive ultrasonic scans to catch this invisible enemy. So when you take a step back and put all of that together, you arrive at a stark contrast. A 20-year-old piece of equipment that's maintained with real discipline is going to consistently outlast a 10-year-old machine that's just been run reactively. The difference isn't the physical asset itself. The difference is the asset management system working behind the scenes. Disciplined asset management easily outlasts reactive panic every single time.
Section 2. The deferred maintenance trap, the multiplier effect. Now, deferred maintenance is rarely a decision made in total isolation, right? It's usually the result of competing priorities, tight budget constraints. But we have to ask the hard question: what does waiting actually cost us? Putting off necessary upkeep might look like savings on this month's spreadsheet, but deferred maintenance doesn't just delay a cost, it actually multiplies it. Let's look at the nonlinear math behind what really happens when you decide to wait. This brings us to the famous 1 to 5 to 200 rule in asset management. It's a devastatingly simple ratio. For every €1 you don't spend on preventive maintenance, the corrective repair is going to cost you about €5. But wait, it gets worse. If that failure results in a production impact or, heaven forbid, a safety incident, the total consequence cost can skyrocket to €200. It brilliantly and painfully illustrates how procrastination breeds massive financial and safety consequences.
Let's actually look at a real-world example of this slow-motion car crash. It's called a cascading component failure. Step 1, you skip a simple €40 coupling replacement. Okay. Step 2, that worn coupling creates an operational imbalance, transferring shock loads directly to the adjacent shaft bearings. Step 3, those bearings heat up, they score their housings, and suddenly you're looking at a €2,000 bearing and housing overhaul. Just like that, one deferred component failure propagates right through the entire machinery train.
And on top of all that, you pay what's called the reactive premium. Finance teams understand this all too well, even if maintenance teams sometimes struggle to articulate it. Emergency parts. They cost 20 to 40% more just due to short lead times. Emergency labor. Go ahead and add 50 to 100% for overtime and contractor callouts. And then there's the real killer, production loss. If a line outputs €10,000 an hour, a 4-hour stoppage means a €40,000 exposure, even if the direct repair itself only costs $3,000.
Section 3. Tracking the degradation curve, making the invisible visible.
To fight back against this exponential decay, we have got to rely on data-driven frameworks. We can't manage what we can't measure, right? The absolutely most crucial leading indicator is MTBF, or mean time between failures. When MTBF starts declining across an equipment class, it is a massive red flag signaling accelerated fleet degradation. For example, if your centrifugal pumps on abrasive slurry duty are failing at 60% of their designed MTBF, that doesn't just mean bad luck. It means your inspection intervals must be compressed immediately to match the actual operating conditions. The manufacturer's original specs are really just starting points, not rigid laws.
To manage this effectively, we use the PF interval framework. P is the point where a potential failure becomes detectable, and F is the point of actual functional failure. So for corrosion, the PF interval might be 24 months, but for a bearing vibration anomaly, you might only have 6 weeks before total failure at day 0. Intervening within this specific window allows for condition-based life extension. This totally beats the old bathtub curve assumption that machines just have a hard expiry date. It's really all about catching the failure while it's happening, but before it actually breaks the machine.
Section 4. The CMMS solution, the data-driven cure.
Without a computerized maintenance management system, a CMMS, you are essentially flying blind. You're trying to manage incredibly complex degradation using just your intuition, and intuition costs you heavily. Operating costs for aging industrial equipment typically run 25 to 40% higher than modern assets. Why? Because of increased maintenance frequency, energy inefficiency, and unplanned downtime. Older assets are going to rapidly drain your budgets when they're managed purely on instinct instead of hard data.
So, what does a proper data structure actually look like? Well, let's look at a platform like ManWin-Win, which provides the exact framework needed for industrial environments. It bridges the gap between those lightweight, basic software tools and the super heavy, 6-figure enterprise suites. It gives you the essentials: complete asset registers based on criticality, condition-based preventative maintenance scheduling, rigorous failure mode and MTBF tracking, and detailed total cost of ownership comparisons. This is the foundation of actually tracking the decay we've been talking about. And having that data allows you to apply the vital total cost of ownership, or TCO rule. You can finally answer that age-old question, when do we replace this machine? The rule is actually pretty clear. Replace when the maintenance cost trajectory exceeds the annualized replacement cost over a 3 to 5 year horizon. A proper CMMS makes this specific calculation visible, effectively stopping the financial bleed in manufacturing industries by replacing pure guesswork with economic certainty. Which leaves us with one final, absolutely critical thought. Take a hard look at your own facility right now and ask yourself, is your current state of reactive maintenance truly sustainable? Are incomplete asset data and decisions made without trending information really protecting your bottom line, or are you secretly falling victim to the invisible disease of asset degradation? The data strongly suggests that waiting to hear the failure is the most expensive maintenance strategy of all. Thanks for joining me on this explainer. Keep asking the right questions and stay curious.